If you're really into math, I bet you have seen this statement before. E to the I pi power plus 1 is equal to 0. This thing just doesn't make sense to you. What even is I? How in the world are these three things getting scrambled together to become -1? It just doesn't make sense at all. Yet, in this lesson, I'm going to cover everything from the basics, the origin of I, to all the way down to the full version of this. This is just a special case of that version, to the full version, which is just even more impressive. And everything is going to look natural. So natural that you think you can do it yourself. Let's dive in together. So to talk about this, we must begin by analyzing the quadratic equation. Ax squared plus bx plus c is equal to 0. We know the solution is x is equal to -b plus or minus b squared minus 4ac over 2a. But what happens when b squared plus 4ac is less than 0? It is undefined, to an extent at least. But in reality, we will define something as the imaginary unit. I squared is equal to -1. This just can't happen in real numbers. Well, now we can essentially represent every possible negative square root. For instance, the equation x squared plus 2x plus 2 can be solved as -2 plus or minus -4 over 2. So that is -1 plus or minus I. And from this example, you probably noticed that imaginary numbers must be used together with real numbers to form something special that can actually represent a root of every possible quadratic equation. So in this case, we introduce complex numbers. Complex numbers consist of real numbers plus a real multiple of the imaginary unit, or this right side here is an imaginary number. So a is equal to the real part of z, as we say, and b is the imaginary part of z. And that's essentially all you need to know about the origin of complex numbers. Now, into the operations. So for addition and multiplication, just treat I as a variable. And after you calculate everything, use I squared is equal to -1 to simplify. As for exponentiation, it is quite simple. For instance, let's just take I, for example. I to the first degree is simply I, and then I squared is equal to -1. I to the third degree is equal to I squared times I, so it is actually equal to -I. And I to the fourth degree is equal to 1 because it is I squared. And you repeat, I to the fifth degree is again just normal calculation, I to the fourth degree times I, so I to the fifth degree is I again. So in this sense, exponentiation as with imaginary numbers or complex numbers as a base, it is just the same as real numbers. However, when you put exponentiation up to the exponent, it's going to get crazy. For instance, I to the ith degree, what even is that? This is what we're going to deal with in a moment related to e to the I-th degree. It is something similar because I is up here in the exponent again. The reason that this is slightly complicated is just what even is I copies of I? What even is I representing? It just doesn't really make sense. So before we dive into that, let's first analyze complex numbers, their properties a little bit more. Set z is equal to a plus b. And I hope by now you have already realized that a special thing about complex numbers is that they're defined by two numbers a and b. That means you can represent any complex number using a number pair. And then in this case, a number pair just looks like a dot on the plane, so we introduce the complex plane. This is the imaginary axis, and this is the real axis. And for instance, in this case, let's plot z is equal to 1 plus 2i. Then in the real axis, it is equal to 1, or x is equal to 1, and then the imaginary axis, or y, should be equal to 2, so this point is z, and we're done. That's just how simple it is. And then, a natural thing to wonder about points is, what is the distance? Let's denote the distance from z to the center as this, or the modulus of z. Here, the sign outside is not the absolute value, nor is modulus related to modular arithmetic in number theory. It is just a way of calling it. It is just the distance of z to the center. Then, in this case, it is equal to square root of a squared plus b squared, right? And there's something interesting about this, which is this thing, it can be factorized. Ever since we learned complex numbers, we can now factorize sum of squares as well, whereas before we can only factorize sum of difference of squares. But essentially, you're just substituting plus b squared to minus bi squared. This is the key step here. But then you factorize it. And the interesting thing is z is showing up. Here it should be a minus bi, sorry. And then, in this case, z multiplied by a very special number, something specially related to z, just gives the modulus, squared, of course. In this case, we define the right side as the conjugate of z. The definition is simply z is equal to a plus bi, then the conjugate is equal to A minus BI. In this case, note that Z times the conjugate of Z and Z plus the conjugate of Z is both real, despite Z being complex numbers. And this is the unique number of this property. So again, something interesting, and we also have the formula. The modulus of Z is simply equal to the square root of Z times the conjugate of Z, or we add the square here. And that's all we need to know about the complex plane. But actually, there's something more that I would like you to prove yourself, which is in fact Z minus W, where W is just another number on the complex plane. Your task is to prove that in fact this modulus is simply the distance from Z to W. Try it yourself. Now it's high time we tackle some interesting problems. To begin with, and relatively easy, but something that really require your fundamental basics of complex numbers, a problem from AMC12, difficulty 2. So this polynomial, despite having degree 6, only have 4 distinct roots. So that means some roots are covering each other. We are to find the modulus of C. In this case, solving x squared minus 2x plus 2 gives the solution x is equal to 1 plus or minus I. And then the second thing, x squared minus 4x plus 8, gives the solution x is equal to 2 plus or minus 2I. And then what next? Let's analyze x squared is equal to cx plus 4. We know that this is x minus r1 times x minus r2, giving 2 solutions. And since all 4 solutions is already obtained, r1 can't be something new. Also, r1 times r2 is equal to 4. So the product of these two numbers is in fact real, suggesting that r2 is a multiple of the conjugate of r1. And also notice that their modulus is also 4. So that means r1's modulus times r2's modulus is equal to 4. In this case, the modulus for these solutions are square root of 2, and this is 2 times square root of 2. So r1 must be selected from the first one, and r2 meantime should be from the second one. And since r2 is the multiple of the conjugate of r1, that means we can select 2 possible pairs. So both gives 3 plus or minus I, which has a modulus of square root of 10, and we are done. That is just basic complex numbers. And again, we are still focusing on moduluses because essentially for the complex plane, this is 1/2 of the most important thing in complex planes. Now, in the second problem, we are tackling a really interesting problem related to moduluses. And when you see this, I bet the first thing that jumps up in your head is the modulus of Z squared is Z times the conjugate of Z. In this case, let's simplify the above equation. First of all, let's tackle it term by term. The left-hand side is simply 12 times Z times the conjugate of Z. And then the right-hand side requires some analysis. Because first of all, Z plus 2, what exactly is the conjugate of Z plus 2? The conjugate is simply Z's conjugate plus 2. You can verify it yourself. And that means the first term in the right-hand side is simply this. What is the second term then? Similarly, you notice that the second term is simply the conjugate. The second term is simply Z squared plus 1 times the conjugate of Z squared plus 1. And then the last term is the constant term, 31. You can verify this yourself. The conjugate of Z squared plus 1 is in fact the conjugate of Z squared plus 1. And then in this case, reorganizing a great deal, you are equating the left-hand side and the right-hand side. In the end, you form the following expression by solving for real numbers, because we know that the sum of conjugates are real, the product of conjugates are real as well, so both equations are 0. Then this is -2, this is 6. And admittedly, it is not all that easy, because the process of simplification requires some work, and it requires your ability to recognize the squares. But this thing is so important in solving equations. As I mentioned in lesson 2, we already saw a problem related to finding squares, but it's so incredibly important that you really do need to have the ability to notice them. And then in this case, 6 over Z is simply the conjugate of Z. And so we're essentially trying to find Z plus the conjugate of Z, which is -2, yielded over here. And truthfully, if this is the only solution, it wouldn't be that easy. However, notice that there is a 6 over Z. And the original problem shows that all answer choices are real. So that means most likely 6 over Z is simply the conjugate of Z. And this simplifies things down a lot because you can just guess that this is the conjugate of Z. So in that case, it will be a difficulty 3 problem. But if you're just not given that the answer choices are all real, then this would be a difficulty 4 problem, if you ask me. It is not an easy problem, especially the step down here of reorganization. Okay, now before we move on to problem 3, which you are seeing, we need to explain a bit more about the complex plane, because at this moment we have only mastered half of the complex plane. This, in fact, in my opinion, is the only step in this lesson that is not intuitive, which is talking about vectors. But if you have seen vectors before, it is going to be very intuitive and very natural. However, vectors are not included in AMC12. In this case, when you think about a point on the plane, that would be a plus b, and then suppose you apply this point to another point, whatever that means. Suppose there is a point here. Then you're applying this point by adding the values. This originally is x0, 0. Then you're adding the values to obtain a new point, x0 plus a and b. This is very similar to when we treat things as 1D. Suppose there is a point. Then when you add something, in reality, you're actually just moving the point to a new point. Then in this case, we can add a point to obtain a new point as well. So this is described as a vector, which essentially describes movement. This is the vector, and then when you apply the vector to this point, you move the point. In this case, it can be similarly treated for complex numbers as well, because complex numbers are also points on the complex plane. Now, describing a vector, generally, we do not describe it using a comma b. There is another way to describe it, which is describing the angle from the x-axis and the length of the vector. It just makes a little more sense because you know what direction you're moving and by how far you're moving. In this case, let the angle be theta, and the length of the vector be r. Then the point can be written as r times cosine of theta and r times sine of theta. I think this isn't too hard to understand if you're aware of the unit circle of trigonometry already. Now, for complex numbers, it can be similarly written in the form z equals r times cosine theta plus I times sine of theta. Or, for short, this can be represented as the modulus of z times EIS of theta, which is just cosine of theta plus I sine of theta. These are equivalent. It's just an abbreviation. In this case, we by now know how to treat points as vectors. Let's now examine some problems. To begin with, problem 3, difficulty 2. We are given a set of complex numbers such that they are the sum of two complex numbers z1 and z2. z1 is in the complex plane and lies on a segment. One side is 3, and up there it's 4. You can then connect them. This is the segment. And then we are also given z2. z2 is on the circle or inside the circle with radius 1 because the magnitude is at most 1. It is this region. And then, now you're asked, what is the area of R, which is the sum of z1 and z2. Now we treat z2 as a vector. So suppose we just focus on this vector. What happens when we apply z2? Then you're shifting everything to the side by a little bit, by 1. Similarly, you can do the same thing for other directions. You would get a graph that looks somewhat like this. So first of all, there is of course a circle at each end of the segment, and then for each other part, it is essentially like a racetrack because in each part you can move out a distance of this. This is the true distance. So essentially, you can treat it as a triangle with length 5 and 2 because the radius is 1, so the diameter is 2. And then also two half circles placed over here with radius 1, and the problem is solved quite smoothly. After all this toil, I think it's time we go back to the problem we left down before. We mentioned that addition is easy. What about multiplication? In complex numbers, the basic operations are very easy. It is just we do the same thing as real numbers. For instance, in this case, let W be A plus BI, Z be C plus DI. And you can just add them together. For addition, then that would mean A plus C plus B plus DI. This makes a lot of sense. For multiplication, however, it gets a little strange because if you multiply it term by term similarly, you would get the result of this, and this doesn't make as much sense as addition. So I guess it's time now that we go back to the problem we left down before. It's time that we deal with multiplication to give it a more intuitive meaning than this. The way to start here is you first do some experimentation, and then at some point you might have noticed that, for instance, the point this, when you try to multiply it, let's just say square it because that's the most basic version of multiplication, you get 2i. Now let's plot these 2 points and see if there is anything special about them. 1, 1 is here and 0, 2 is there. What is special about these 2 points? If you're really good at pattern recognition, you might have said, okay, these 2 angles are the same. And then, if you're even better, you're going to notice that the modulus here is square root of 2 and the modulus here is 2. So we can guess when we square a complex number, z, which is equal to r times cis of theta, where r is the modulus, what happens is z squared is r squared times c is 2 theta, or in other words, you're just trying to square this, which means r squared times cis squared of theta. what exactly is this thing squared? After some manipulation, you can indeed notice that this is true by using some trig identities. But now, before we dive into that, I am going to mention something, which is we will be coming up with three different things. The theorem I'm trying to talk about right now, the mysterious theorem, the thing related with e to the I pi degree plus 1 equals 0, or the full version of that theorem, and then trig identities. These three things are in fact interconnected. What that means is using the full version, you can prove the mysterious theorem, and similarly, you can use trig to prove the mysterious theorem. Also, you can use this mysterious theorem to prove this theorem, and then you can also use the mysterious theorem to prove basically every single trig identity. That is very interesting in my opinion. In this case, we are going to assume the trig identities that we haven't covered yet in this course are true. And in this case, the way to prove trig is we're using geometry to prove these identities and just claiming that these extend to essentially every single point. And this extension actually works and can be proved as well. So of course, what I'm saying is that in this case, we're going to assume the trig identities are true, and we will prove them using geometry and the unit circle later when we talk about triangles. And then since we assume this is true, then we can prove the mysterious identity, the mysterious theorem over here, and with that we can conclude to our result of e to the I pi power plus 1 equals 0. Let's see, back to this example. We are trying to find cosine of these two CIS of theta squared. And let's just go one step further and call it to the nth degree. We're guessing that this is true. This is the theorem we're trying to prove. V to the nth power is equal to its modulus to the nth power, and with a degree multiplied n times. In this case, we can prove iteratively. What we're claiming is that if we multiply this thing by another angle b, then this is just cosine of a plus b plus I of I sine of a plus b. And the way to prove this here, I have already placed it in the materials down below, so you can check it out yourself. And then applying this repeatedly, because at first let a be theta, and then b is also theta. Then after we apply that, a plus b is 2 theta, right? Now we let a becomes a plus b, and then we apply b equals theta again. That means we have now proved that for 3 theta it also works. Then repeatedly, in the end we can prove for n theta it also works. So essentially, by this trig identity, we can prove iteratively that cosine theta plus I sine theta to the nth degree is cosine n theta plus I sine n theta. And in that case, this is proven. So this is the De Moivre theorem, which states when z is equal to its modulus times cis of theta, then z to the nth degree is equal to the modulus to the nth degree times cis of n theta. And by now, you have probably realized why some people say complex numbers are related to rotations. For instance, if we plot the point I on the complex plane, then when we square it, it is essentially moving 90 degrees over to -1. And then repeatedly, when we multiply it by I again, we get -I. Then multiplication again, then we arrive at 1, and this forms a loop. And of course, there are numbers also apart from I. For instance, does there exist a number where you just have to rotate 3 times to obtain 1 again? Of course there is. The number is located somewhere here, such that the degree here is 120 degrees. And then after the first time, it lands down here because it's 120 degrees, then lands at 1 after multiplying by that value again, which arrives at 1 again. These are roots of unity, and we'll go into that a bit later, which essentially is values where z to the kth degree ends up being 1. Because after all, in any number system, the unit is always very important. However, we'll go deeper into that in a moment. Now, our task is to finish the link and actually prove why this is true. Recall e to the tth degree is equal to the limit of taking n to infinity, and then the value specifically is 1 plus t over n to the nth degree. And then in this case, even though t we're simply referring to real values, what about we just extend the definition? We extend the definition so that we define e to anything, even if it is imaginary numbers, it is still okay. Just anything as its exponent is going to be defined like this. This solves the difficulty of raising something to an imaginary exponent or a complex exponent. And then in this case, we just have to plug it in, which looks like this. Now, let this part be
a complex number that we are focusing on. First of all, we want its modulus, or the square of its modulus, because it is going to be a little easier to calculate. In that case, since this number can be treated as 1 plus theta divided by n times I, so the real part of z is 1, the imaginary part of z is theta over n, then the modulus squared is simply 1 plus theta squared divided by n squared. And then we also need the angle of z to the x-axis. We denote this as arg z, or argument of z. It is arc of theta over n. Or more exactly, you can think about this number as here and there. So the y value is theta over n. Then what is the angle here? We know the angle, let's say this angle is alpha, and tangent alpha is equal to theta over n divided by 1. So that is essentially saying alpha is arc theta over n, whatever, that is just the reverse way of calculating. So we can plug this thing back in. And then this is the setup we have with z. Now we also know, now we can proceed to calculate what exactly is to the nth degree. Like there is an exponent of n there. First, let's find the modulus of z to the nth degree. That is just the square root of 1 plus theta squared over n squared to the nth degree. What is that? I have to tell you, when n approaches infinity, this thing approaches 1. It is different from previously what we had here. And an analogy can be harmonic series and the 2 series. So previously we discovered that this is divergent, but when we square it, it becomes convergent, or 1 squared plus 2 squared. But that thing is convergent, while this is divergent. So essentially, a squared thing in the denominator can cause the thing to be more likely to converge. In this case, it in fact converges to 1. I'm not going to prove it directly because it's related to limits and another math area that we haven't covered yet, but just take it for granted, okay? And then also, n times arc z is equal to n times arctangent of theta over n. And this thing, in fact, approaches n times theta over n, which is equal to theta. I'm not going to prove it yet again because it is not what the topic is. But you can just have a feeling of when we keep on applying an infinity exponent to a complex number, essentially that is what's going to happen. And then that means z to the nth degree is in fact 1 times cis theta, which is cosine theta plus I sine theta. Of course, in this case, given sufficient knowledge with limits, and thereby the natural exponent, you can arrive at this conclusion yourself. There's nothing too complicated here. Then that means this is in fact equal to e to the I theta power. This is the Euler's theorem. Now, the more famous version is simply plugging theta equals pi. In this case, cosine pi is equal to -1. I sine pi is simply equal to 0. So this term cancels off. That means e to the I pi power is exactly -1. So plus 1 is equal to 0. QED, we have proven it. Great job. Finally, I have satisfied your curiosity, and now we can get back down into the ground of roots of unity. In fact, in my opinion, this is one of the most interesting parts of complex numbers, at least in AMC12. And we're just going to tackle a problem, and we will try to discover the answer of the problem and thereby the roots of unity while analyzing the problem. So, problem 6. We're given a polynomial and its roots. We are to find all its coefficients. That's all we have here. It is very clear for you if you have watched my polynomials video that a is equal to negative the sum of roots. Let's write it r plus s plus t. And then b is rs plus rt plus st. And then c is negative rst. We just have to find all those values. However, even the simplest, which is r plus s plus t, just doesn't work, because how can you add cosine values? We don't know. In case you're wondering if there's any trig identities we can work with, no, unfortunately not. This problem is not associated with any trig identities. It is simply a problem related with complex numbers, even though the complex stuff is hidden. So how can we discover where it is hidden? Let's just focus on the same thing that those complex numbers have and trig have, which is the unit circle. This is our complex plane, and we have the unit circle right at its center. Now, let's try to find where these three values are, and that means we have to divide the circle into separate parts. So the cosine values then are cosine 2 pi over 7 over here, cosine 4 pi over 7 near the middle, and cosine 6 pi over 7. Now, what can we do to these numbers to actually arrive at something? Since we mentioned roots of unity previously, let's just check if these things are roots of unities. And in fact, they are, because it is just separating the entire circle into 7 parts. So if we repeatedly add these stuff together, if we repeatedly multiply some value by, say, this complex number, then you're just going to get a rotation that is 360 degrees divided by 7. After rotating 7 times, you arrive at 1, 0. So these are in fact roots of unity. Since we are considering roots of unity, let's fill in all 7 roots of unity. This is the first. We'll denote it as Z1, and this is Z2, Z3, Z4, Z5, or even here you can write it as Z0 or Z7 or simply 1. Anything works. Now, in this case, you might notice that, interestingly, both the real parts of Z1, Z to the first degree is equal to the real part of the 6th degree of Z, which is equal to cosine of 2 pi over 7. And also, Z1 and Z6 are pairwise conjugate. So what can you arrive at here? If you're really smart, you're going to realize that Z1 plus Z6 divided by 2 is exactly cosine 2 pi over 7. That's an important insight. So under this logic, we can say let Z be equal to E to the 2 pi I divided by 7th power. And this is essentially this guy over here. You can check this yourself by applying the Euler's theorem. And then with that, we can represent the cosine values. Cosine 2 pi over 7 is equal to Z plus Z to the 6th degree divided by 2, and then 4 pi, and then I will just list the rest out. Here we go. And now we can find this. So we know this is actually simply negative the sum of j equals 1. I'm not going to use I as the index anymore because we have the imaginary unit. J equals 1 to 6 Z to the jth power divided by 2. Next, we will try to find these values. And in fact, it isn't too hard. So I won't give the entire calculation here, but essentially, if we denote S equals the sum of Z all the way up to Z to the 6th degree, then ABC is simply S squared over V2. You can derive this step by step yourself. And this is actually the good part about using complex numbers to represent trig values, because these things, when they get multiplied or squared, they tend to be of a very good shape. For instance, in this case, this conclusion here is very neat. But then the question is, what exactly is S? Now it is high time we think about vectors again. Because if you think about vectors, then addition is simply putting a vector's tail to another vector's head. So that means we can begin with z0. And let's just add in the z0 to the end and remove the 1. After all, z0 is also a root of unity. And then we have z1 that moves like this. And then z2, z3, that goes like that, z4, z5, and then finally z6. So in fact, it is just a heptagon. And so the sum of all these things together is 0. So that is actually a very important identity. The sum is 0. So that means S is actually just simply equal to -1. So the problem is solved because S squared is 1, then ABC is 1 over 32, and we are done. This is a classic difficulty 4 problem that requires some creativity and a bit of algebraic manipulation. So really a good problem, in my opinion. Now, we have successfully concluded today's video's problems. The practice problems ends here, but now let me show you homework, because there's some important problems that will help you get a better understanding of imaginary numbers, of complex numbers. So first of all, you will have to prove this. This is very important, a very important identity, and we have already proved this in the lesson, so ignore that. And then next, I crafted a very simple problem myself, and I'm essentially asking you to find the value z such that it satisfies these constraints. After you prove the last problem, this one, I think it's going to be very easy. Remember, I here is not any random variable, it is the imaginary unit. And also, I would like you to practice doing some transformation between complex numbers of their A, B form to their polar form, which is an important skill as well. Finally, I selected a few problems from AMC12. This one is a nice problem related to the complex plane, and you can just experiment about on the complex plane and see if you can discover anything interesting. The last problem here is designed to test your skills with polynomials with roots that are imaginary. For example, choice C, there is no real roots. So you can test your skills out of it. And this problem is a little challenging in my opinion. So I gave you some hints. First of all, you can try to rewrite this thing. There's a nice way to simplify it further. And then also, it is very important that you are exceptionally careful with certain situations. What exactly, I won't say, but when you finish rewriting this thing, you will see a special situation where there are some special details that you need to be exceptionally careful about. Very mysterious words, but that is just how things go. That is all for today's video. I hope you understand complex numbers now. Some of the proofs is a little difficult because complex numbers, they are frontier math, so it is natural. But I think you by now can grasp the outline of how complex numbers are developed. And that is what is truly important for your journey in math. So I hope you enjoyed, and I will see you 2 days later, and we will start talking about geometry. Bye.